Hello, welcome to the rfnoc-4 workshop. My name is Neil Pandia. The workshop is divided into two parts. I'll be presenting the first part, and my colleague Jonathan Pendlum will be presenting the second part. This presentation has been updated for the new UHD and rfnoc version 4, as well as for GNU Radio 3.8. There are further updates that will be made to this presentation several weeks after the GNU Radio conference that will include various changes and enhancements. Before watching this presentation, we recommend that you first check to see whether an updated version of it has been posted on the Ettus Research knowledge base. In Part 1, we'll introduce the rfnoc-4 framework and give an overview of its architecture and highlight what's new in version 4. We'll then show a demonstration of rfnoc in action. In Part 2, we'll take a deeper dive into rfnoc and look more closely at the software architecture and the hardware FPGA architecture. We'll then go through an exercise of creating a new rfnoc block from scratch and integrating it into UHD and GNU Radio. Let's start by taking a look at the current situation of SDR processing. Most often, SDR applications run on the General Purpose Processor, or GPP, or just simply the CPU, or the host computer. This can be a laptop as shown in the slide, or a server computer running on an Intel CPU, or an embedded computer running on an ARM CPU. Applications can be written in many different languages and tool chains, such as C++, Python, and GNU Radio. For those of you who are new to GNU Radio is an open source framework for SDR signal processing. Programs in GNU Radio are called flow graphs. Flow graphs can be written in C++ or Python and can be constructed visually using the GNU Radio Companion or GRC tool as shown in the screenshot. The CPU takes advantage of multiple processing cores, as well as instruction sets that support parallel data processing, such as SSE and AVX on Intel CPUs, and Neon on ARM CPUs, in order to accelerate processing. Some applications leverage the GPU to accelerate processing using libraries such as OpenCL and CUDA. One popular example is Phosphor, shown here in the screenshot, which displays a real-time GPU-accelerated spectrum display. Increasingly, applications are using the FPGA to accelerate processing. The FPGA is attractive for several reasons. First, it provides dedicated hardware resources, so it is capable of handling especially high data streams, supporting very wide bandwidths. Second, it is also well positioned in the signal chain, being close to the antenna and data converters, closer than the GPU, and does not necessarily require support from the CPU to operate. These features make the FPGA ideal for many operations, such as sample rate conversion, filtering, and channelization. The table on this slide shows the resources and clock rates for the FPGAs in successive USRP devices. The Generation 1 FPGA was small and slow, and there was no space for any user-defined logic. The Generation 2 FPGAs were somewhat faster and larger, and provided at least some resources for the user-defined logic. The Generation 3 FPGAs are faster and larger still, and provide significantly more resources for user-defined logic. The trend is that FPGAs are getting faster and are providing more and more resources that can be used by SDR applications to accelerate processing. And we're really at a point these days where significant user-defined logic can be added to the FPGA. Let's illustrate the challenges in SDR processing. The screenshot at the bottom of the slide is from a GNU Radio flow graph which implements Welch's algorithm for power spectrum estimation for 200 MHz of bandwidth on a single channel of the USRP X310 radio. There are significant processing requirements on the CPU in this application. An FFT, magnitude squared operation, and a move ring average are to be performed on the data stream at 200 megasample per second. And in addition, a graphical widget is to be displayed showing the result in real time. Note that the math in this application can be parallelized, and so it is a good candidate for being done on the FPGA. The mathematical operations are one of the things that heavily load the CPU. The other is the real-time consumption of IQ samples from the radio at 200 megasample per second. This represents 6.4 gigabits per second, which is in itself a heavy load for the CPU to sustain. With such a heavy load as this, the CPU will face additional challenges around latency and determinism, which are often critical to some applications. It could become difficult to achieve precise timing and maintain proper data flow. The FPGA can help with all of these challenges. All the USRP radios have an FPGA, and recent devices have larger FPGAs that can provide significant additional horsepower. The FPGA code is open source, the schematics are openly available online, and the host side driver is also open source. So with all of these capabilities, why then don't more people use the FPGA? As a side note, the photo on this slide shows the X310 motherboard, and the large black component on the right side is the heatsink for the FPGA, which can actually run very hot. Well, compared to the CPU and even the GPU, FPGAs are harder to use and are slower to develop on. There are many challenges and factors to consider that don't exist when programming the CPU or the GPU. Not as many engineers are familiar with FPGA programming. Many engineering curricula do not include any FPGA programming topics or courses. Doing math on hardware is hard. It's much easier to implement the math for an algorithm on the CPU. Often engineers specialize and focus on particular skill segments, such as theoretical algorithm development, software engineering, and FPGA design. It's difficult and uncommon for an engineer or a team to have capabilities in all these skill areas. The goal with the rfnoc framework is to make FPGA acceleration more accessible on the USRP platform. rfnoc provides both software infrastructure and FPGA infrastructure to facilitate integrating user-defined functions and logic through standard and straightforward interfaces. The infrastructure is transparent to the user and enables the user to trade off between flexibility and resource utilization. The rfnoc framework is open source and can be used directly from C++ and Python, as well as from GNU Radio. The upper part of the slide shows a screenshot of a GNU Radio flow graph that implements a real-time spectrum display. The lower part of the slide shows a diagram of the rfnoc framework. The red dotted line indicates the boundary between the host computer, the CPU running the UHD driver, and the FPGA. Users implement their custom logic, or IP, in the form of a compartmentalized rfnoc block. Multiple rfnoc blocks can be instantiated, and it's easy to add and remove blocks. The rfnoc radio block provides the connection between the FPGA and other components in the radio, such as the RF front end, the ADCs and DACs, and the GPIO. For receive operations, IQ samples are output from the rfnoc radio block. For transmit operations, IQ samples are input into the rfnoc radio block. The NOC core connects all the components in the rfnoc framework, such as the I/O interfaces for Ethernet and PCI Express, the rfnoc radio block, and all the rfnoc blocks. All data in rfnoc is passed in a packetized format, so the NOC core is essentially a packet switch. The NOC core is fully connected, meaning that each component connected to the crossbar is connected to all other components connected to the NOC core. The NOC core also supports static routing between blocks and is auto-generated based on the topology of the various rfnoc blocks in use. The name of the framework, rfnoc, or RF Network on Chip, comes from this architecture. The Ethernet MAC and PHY interface provides the connection to the host computer over 1 gigabit Ethernet, 10 gigabit Ethernet, PCI Express, and Aurora. Multiple parallel Ethernet interfaces can be instantiated depending on the particular radio, and the conversion to one of the supported protocols is done automatically. On embedded devices, it provides internal connections to the Zinc ARM CPU. Although the Ethernet MAC and PHY interface is connected to the NOC core, it is not treated like another rfnoc block. The rfnoc API in the host-side UHD driver provides a way for the framework to be configured from the software application program running on the CPU. It provides an interface for the user application program to send and receive data to and from the rfnoc blocks, and also to control rfnoc blocks by reading and writing user-defined registers in the rfnoc blocks. The user application program running on the host can be a standalone C++ program, or a Python script, or a GNU Radio flow graph. Let's consider the example of plotting frequency spectrum to see how rfnoc is used from within GNU Radio, and to see what the data flow looks like. As mentioned earlier, IQ samples are input into and output from the rfnoc radio block. In GNU Radio, the rfnoc radio block is represented by two blocks, the rfnoc-tx radio block for transmit and the rfnoc-rx radio block for receive. The corresponding data flow on the FPGA is illustrated by the solid red line in the diagram. Recall that all data flow between blocks and the host computer must pass through the NOC core. Notice that in GRC, for the flow graph, the arrow from the rfnoc-rx radio block is green, to indicate that the data transfer is occurring on the FPGA and not on the host. Now, let's assume that we want to move the FFT operation from the CPU to the FPGA. To do this, we would instantiate an rfnoc FFT block in the flow graph, instead of using the host-based FFT block. Note that the arrows in the flow graph around the FFT block have changed from black to green, indicating that the data flow is occurring on the FPGA. An FPGA bitstream that includes an rfnoc FFT block must already be loaded onto the FPGA. The corresponding data flow on the FPGA is illustrated by the solid red line in this diagram. The rfnoc framework now supports static routing between blocks, and so the connection from the rfnoc radio block to the rfnoc FFT block could be changed from dynamic to static, resulting in lower latency in the data transfer, as indicated by the dashed black line in the diagram. If it's decided that additional blocks should be run on the FPGA instead of on the CPU, then those additional blocks can be instantiated in the FPGA and then connected either statically or dynamically in GNU Radio. Let's take a closer look at the internals of an rfnoc block, as shown by the diagram here. Again, the red arrows indicate the data flow. So here we have received IQ samples coming from the ADC into the rfnoc radio block and being routed to the rfnoc FFT block. Recall that all data is packetized in rfnoc, so every block has a depacketizer and packetizer at its inputs and outputs respectively. There are also FIFOs for flow control, unless static routing is being used. All the items in green are automatically provided by the rfnoc framework. The item in pink is the user's custom logic, or IP, and is provided and defined by the user. The user-defined logic, or IP, interfaces to the rfnoc framework through an AXI stream interface. As long as your IP speaks AXI stream, then you can integrate it into the rfnoc framework. AXI stream is an industry standard. It is not a proprietary standard from National Instruments or Ettus Research. AXI stream is widely used, and there are many third-party IP cores that use it. There are several options for creating or supplying the user-defined IP. Users may certainly write their own custom IP in Verilog or VHDL. Users may also use IP from Xilinx, since Xilinx Vivado is used to build FPGA images. There is a free open source IP available from opencores.org, as well as from Theseus cores. Many third-party companies provide libraries of IP that can be used and integrated. It is also possible to use Xilinx high-level synthesis, or HLS, to auto-generate Verilog and VHDL code from C++ source files. Each rfnoc block is clocked in its own separate clock domain. This clock domain may be the same as the rest of the design, or it may be different. This can sometimes be useful to improve processing throughput, as well as to help meet timing constraints when building the FPGA bitstream. The block's interface to the NOC core contains FIFOs which handle the crossing between clock domains. Let's consider a hypothetical example of a cognitive radio. Here we have IQ samples received by the rfnoc radio block being routed to the rfnoc FFT block. In this example, the FFT block comes from the Xilinx IP library. The resulting spectrum is then sent to the spectrum policy block, which presumably analyzes the spectrum, looking to raise an alert based on some criteria or trigger condition. When the spectrum policy block sees something of interest, say for example energy in a specific bin, or energy across multiple bins, perhaps averaged over some time period, it then sends a trigger command to the TX modulator block, which in this example was created from C++ code using Vivado HLS. The TX modulator block receives the trigger command, and it obtains a payload of specific IQ samples from the host computer. Upon receipt of the payload, the TX modulator block then immediately transmits those samples by sending them to the rfnoc radio block, with some prescribed sampling rate, RF frequency, and gain value. The example is meant to illustrate that the latency in the system's response to the trigger condition is much lower when implemented on the FPGA than would be possible when implemented on the CPU, in which case the IQ samples would have to be continuously streamed from the radio to the host computer over Ethernet, and the FFT and spectrum policy functions would have to be performed on the CPU, perhaps within some set of tight timing requirements or time duration. In summary, rfnoc aims to make USRP FPGA programming more accessible to the user. It's tightly integrated with GNU Radio, although rfnoc can also be used without GNU Radio, from a standalone C program or Python script. The rfnoc framework includes a library of blocks from Ettus Research, such as Phosphor, FIR filter, FFT, signal generator, and keep 1 in N blocks. rfnoc is supported on all current third-generation devices, such as the USRP X300, X310, N300, N310, N320, N321, E310, and E312, and will also be used on all future devices going forward. And again, the rfnoc framework as well as the host side UHD driver are completely open source. Let's take a look at what's new in rfnoc 4. The documentation around the rfnoc framework has been improved and is still being expanded. The specification document has been published, and several additional items will soon be published on our knowledge base, including an rfnoc 3 to rfnoc 4 migration guide, a getting started guide, several new application notes, and several reference examples. There have been several software side enhancements made around stability and testing, and there is a new Python 3 support for rfnoc. On the FPGA side, several improvements have been made. The rfnoc architecture has been made more scalable to support and sustain higher sampling rates, and now allows users to instantiate many more blocks than before. It also provides a new static routing capability that enables users to better trade off latency and resource utilization against flexibility, in terms of using static routing versus dynamic routing between blocks. And rfnoc 4 now supports GNU Radio 3.8, which is the most recent release of GNU Radio. I'll now show my screen and run a demo of rfnoc Phosphor, which is a real-time spectrum display tool. The hardware that I'm using is a USRP X310 and a WBX daughter board. The system is running Ubuntu 20.04 with GNU Radio 3.8.2.0. I'll start by running the Phosphor demo from GRC. I'll just run it first, and then I'll come back and explain how the flow graph works. Because I'm using the WBX daughter board, my tuning range is between 50 and 2200 MHz. The tool is named Phosphor because it tries to emulate the persistence and ghosting effects in the displays of the old Phosphor CRT spectrum analyzers from about 20 years ago. Phosphor can be run on the CPU, the GPU, or the FPGA. Here, of course, we're running it on the FPGA. It can also be run as a standalone tool. Here, I'm running it within my GNU Radio flow graph. The upper half of the display is an FFT display, and the lower half of the display is a waterfall display, showing historical information over time. The sample rate is 100 megasample per second, so we are capturing 100 megahertz of real-time spectrum. And since all the math is running on the FPGA, the CPU is very lightly loaded. For example, using Phosphor on an FPGA, you could visualize the maximum 200 megahertz of bandwidth on the X310 radio per channel, and then do that across 2 channels, making 400 megahertz of spectrum total in real time with minimal CPU overhead. You could run that on a very underpowered and inexpensive system. Let's first tune to 568 megahertz. In the United States, the spectrum from 512 to 608 MHz contains ATSC digital TV stations, which are 6 MHz wide each. I'm running this demonstration in New York City. You can see several stations. There is one at 560 MHz, which is channel 29, and one at 578 MHz, which is channel 32. The spectrum shifts and changes a bit as I move the antenna. Next, let's tune to 315 MHz. Most remote key fobs for cars operate at either around 315 MHz or 434 MHz. I've seen a few also operating in the 915 ISM band. You can always check the FCC ID of your key fob to determine what frequency it operates at. The FCC ID for the key fob for my Honda reports a frequency of 313.85 MHz. Notice the phosphor display as I click the key fob. Luckily, modern key fobs use rolling codes. Otherwise, you could simply record the signal and then play it back to unlock the car, without the key fob even being present. Fortunately, with the use of rolling codes, those kind of attacks no longer work. Finally, let's tune to 850 MHz. (850 MHz) is LTE band 5, where from 824 to 849 MHz you have the uplink, and from 869 to 894 MHz you have the downlink. T-Mobile uses band 5. We can see some downlink signals from the nearby base stations called E-Node Bs. It looks like there's one 5 MHz downlink carrier at 883 MHz, and there is some intermittent and ephemeral activity on the uplink between 837 and 842 MHz. Now I'll stop phosphor and come back to GRC and explain the flow graph. The processing starts on the left side with the rfnoc-rx radio block. The received IQ samples are streamed to the rfnoc digital down converter block, or DDC block, at 200 megasample per second, which is the full rate of the X through 10 radio. The rfnoc DDC block decimates that down to 100 megasample per second, and the IQ samples are then sent to an rfnoc FFT block. The resulting frequency domain data is sent to the rfnoc phosphor block, which computes the histogram and the waterfall, which are then sent to two streamer endpoints, and are then sent over to the host computer. Note that the data flow up to the rfnoc phosphor block is on the FPGA, and so the arrows in GRC are colored green. The arrows after the streamer endpoints are colored black, since the data flow there is on the host. The rfnoc QT phosphor display block runs on the host and is responsible for creating and updating the GUI with the histogram and the waterfall displays. Two QT GUI range blocks provide sliders in the GUI for controlling the receive gain and the tuning frequency. Again, the key thing here to note is that all the calculations for the FFT, the histogram, and the waterfall are being done on the FPGA, not on the CPU. And that the CPU is minimally loaded, even for high sampling rates and for large capture bandwidths. You can use rfnoc phosphor to enable the monitoring of large amounts of spectrum in real time on even low-powered CPUs. This concludes part 1 of the rfnoc workshop. My colleague Jonathan Pendlum will now present part 2. Thank you for watching.
Thanks, Neil. My name is Jonathan Pendlum, and this is part 2 of the rfnoc 4 workshop. In part 1, we explained rfnoc 4 at a high level. In part 2, we will examine the finer details of the FPGA architecture, software implementation, and GNU Radio integration of rfnoc. We will also implement our own custom rfnoc block. Occasionally during the workshop, I will point out differences between rfnoc 4 and the previous version of rfnoc called rfnoc 3. Don't worry though if you haven't used rfnoc 3 before. These are just some interesting side notes for experienced users. Alright, so we have a lot to cover, so let's get started. In part 1, Neil gave an overview of the rfnoc framework and how it is split between FPGA and software components. But how do we get these individual components? First, we need to do some initial setup. We need to install the dependencies required and the tools to do FPGA development. In this workshop, I'm going to assume your operating system is either Ubuntu 20.04 or a distribution based on Ubuntu 20.04. For example, you'll see me using Ubuntu 20.04. I provide an example apt install command with all of the required dependencies listed. You should also install Vivado 2019.1, which is the version of Vivado that is compatible with rfnoc-4. To get Vivado 2019.1 to work in Ubuntu 20.04, there's two libraries that you need to install, and I have them listed here. You also need to install the design version, not the Webpack version, even if you're only doing simulations. Now, simulations can be ran without a license, but if you're building bit streams, that does require a full license. I've already installed the dependencies and Vivado, so let's move on to installing the software components for rfnoc. Now there's three components that we need to get. First is the software driver for USRPs called UHD. rfnoc-4 on the software side is implemented in UHD, specifically UHD release 4.0. So here I have some example commands on how to clone the UHD repo and check out the UHD-4.0 branch, and then how to set up CMake, build the software, and then install it. And let's do that together. So first I'll just copy the git clone command and open up a new window. Now I'm assuming that you're going to go ahead and do all of your work in the source directory that is in your home directory. Now, of course, you can put your code anywhere you like, but that's the assumption I'm making during this workshop. We'll go ahead and paste the git clone command, which will grab the UHD repository and check out the UHD-4.0 branch. I'll then go into the repo and then go into the host directory, and we'll make a directory called build, go into there, and then run CMake. And this will set up the make files necessary to build UHD. And if you get any errors during this process, make sure to go back and look at the dependencies and make sure that you've installed them all. That's generally the only way that you should be getting an error here, is if you don't have the correct dependencies installed. Next, I'll run make with -j. In this case, 3. I'm running in a virtual machine, so I don't have a lot of processors dedicated to this. And this process will take quite a while, so I'm going to go ahead and pause the video and then come back when we're done building. Okay, so we're now done building, and I'm going to go ahead and install UHD. The next component that we need to get is GNU Radio version 3.8. So just like UHD, I'll go ahead and clone the GNU Radio repo. Then we'll go to GNU Radio, make a build directory, and then run CMake again. And just like with UHD, the build process takes quite a while. So again, I'll go ahead and skip forward to after the build process, and then we'll install and do the final component, gr-ettus. Okay, now that we're done building GNU Radio, let's go ahead and install it. And the final component that we're going to install is gr-ettus. gr-ettus is used to integrate rfnoc support into GNU Radio. It's an out-of-tree module, and that's maintained by Ettus Research. So let's go ahead and clone that final repo now. And of course we make our build directory. In this case with cmake, I'm going to enable an additional flag, enable Qt. What this will do is allow Phosphor to be built as well if you want to be able to run Phosphor. If you don't care about Phosphor, you don't need to set that flag. Now this builds fairly quickly, so I'll go ahead and just run make and we'll watch it go. There we go. That was entertaining. Let's go ahead and install. Okay, so now we have our 3 parts installed here: UHD, GNU Radio, and gr-ettus. Now, for our custom rfnoc block to be supported in GNU Radio, we installed the out-of-tree module gr-ettus. As part of gr-ettus, there's a tool included called rfnoc-modtool. Now, rfnoc-modtool is a tool that's based off of GNU Radio's gr-mod tool that allows us to create an out-of-tree module. The difference, though, is that it includes additional files that are needed to support an rfnoc block. For instance, it includes FPGA code and the block controller and associated YAML files. And we're going to go through all these files later on. But let's go ahead and use rfnoc-modtool to create our first custom block here. So since we've installed these locally, they should already be in our path, rfnoc-modtool that is. And so if you want, you can run rfnoc-modtool help. If you get this error, depending on your setup, you may need to set up your Python path to include the local Python dist packages directory. So let's make sure I get this right. There we go. Okay, let's try it again. And you may also need to run this command. And there you go. Now we have rfnoc-modtool working for us. So what we're going to do with rfnoc-modtool is we're going to add a new mod. So we'll run rfnoc-modtool new mod. And we're going to call our new mod tutorial. And it's created a directory called rfnoc-tutorial. We'll go into there and then run rfnoc-modtool add. And our custom rfnoc block that we're going to add is going to be a simple digital gain block where we'll multiply an input sample stream by a value that can be changed at runtime. So let's call our block gain. We'll leave this empty, so just hit return. We'll just do the defaults here so we can keep hitting return. Now, I'll explain what the knock ID is a bit later, but for right now, it's just a unique identifier for the block. You can enter one if you want. It's hexadecimal up to 8 digits. Or you can just hit return and it'll create one randomly. I'll just let it do so randomly. And then I'll hit return twice more, so it goes ahead and creates the other to go ahead and skip the block controller generation and skipping the block interface files generation, to not skip those, that is, to go ahead and do the default value, that is, to not skip them. And now we've added a lot of files and we've set up this directory. Now those that are familiar with gr-modtool, most of this should look very familiar. One new directory though is this rfnoc directory. And then inside here is a couple of folders or directories called blocks, FPGA, and icores. So with rfnoc-modtool, we've added files that are custom for rfnoc that we need to be able to get our rfnoc block to work within GNU Radio, and in general with UHD, and to be able to build it, the Verilog source code that's needed so we can build an FPGA image with our block in it. And some other files to define for our FPGA image what rfnoc blocks we're including. So I'll go ahead and go through some of these files real quick, and we go through them in more detail later in the workshop here. So let's first go into the rfnoc directory and go into the blocks directory. We can see this gain.yaml file. That's a block description YAML file. It tells UHD about the configuration of our block. If we go into FPGA, this is where our Verilog source and test bench exists for our rfnoc block. Now we actually have a subdirectory here called rfnoc block gain. So that's our specific gain rfnoc block. If you added another block, you would see another directory in here. So if we go into the rfnoc block gain directory, we can see that we have a couple of Verilog files here and a test bench that's rfnoc block gain _tb.sv. If we go back to the rfnoc directory and we go into icores, we see another YAML file in here. This one is for creating what is called an image core, which is our bit stream for our FPGA. The image core defines what blocks are in there, along with other configuration parameters. And like I said, I'll go through these files in a bit more detail later, but I wanted to give you kind of an overview of what's in here. In the lib directory, we have our gain-impl.cc, gain-impl.h. Those are for GNU Radio. And then we have our gain block control impl.cpp. That's the block controller C++ code that's needed for UHD. And in the include tutorial directory, we have our gain block control.hpp, our header file for our block controller. And then in the examples directory, this gain.grc, which is an example flow graph with our rfnoc block already instantiated and hooked up to a signal source and a time scope, so that way we have a nice example flow graph we can look at without having to create one from scratch. So now that we've used rfnoc-modtool to create our gain block, if we looked at the various files, we'd see that it only contains skeleton code. This code is very simple, and we want to fill it out with the functionality that's necessary for our gain block. Now when it comes to the rfnoc framework, there's sort of three areas of it: the FPGA implementation, the UHD implementation, and the GNU Radio integration part of it. We're going to start at the bottom here, which is with the FPGA implementation, which is sort of the foundation for every rfnoc block. That's where oftentimes the most interesting part of the rfnoc block is implemented. We're trying to do FPGA acceleration here, so it makes sense that a lot of our focus will be on the FPGA code. And we're going to start off by taking a look at the anatomy of an rfnoc block. So this is a high-level block diagram of an rfnoc block, it's FPGA implementation. note at the bottom there's a legend that explains the meaning of each of the signal colors. Starting at the top, every rfnoc block is connected to what is called the noc core. This is a fundamental component of rfnoc that provides a path for block-to-block and block-to-host communication. Internally, it contains logic for routing rfnoc packets, handling flow control, static routing between blocks, and a few other functions that are beyond the scope of this workshop. But if you're interested in learning about them, they are outlined in the rfnoc specification. This noc core is customized for a given rfnoc block topology and is automatically generated by the rfnoc FPGA tools. Here is a block diagram of the internals of the noc core. And it is a little simplified. There are some parts that are left out, but this is most of what's inside there. On the left, we have the transport interfaces that move data to and from the USRP. Specifically, these are interfaces taken from the X310, so we have 1 gigabit Ethernet, 10 gigabit Ethernet, and PCIe. On the far right, we have our rfnoc block. So we have a radio block, 0 and 1. We have a DDC, which stands for digital down converter. There's 2 of them, as well as a digital up converter block, 2 of those as well. And then finally, included in here is our gain block. Now, when you look inside the auto-generated noc core, we can see on the left there is a cheddar crossbar, which is a fully connected crossbar. That means that every port can route to every other port. To the right of the crossbar, we see that we have the stream endpoints. We have 5 of them defined here. The concept of a stream endpoint is new to rfnoc 4. They can be thought of as points where streams start and end. And this concept will be better illustrated later on in an example in the upcoming few slides. To the right of the stream endpoints, we have the control crossbar and a static routing block below it. The control crossbar is another new concept for rfnoc 4. Control packets go into the control crossbar, and it's also another fully connected crossbar, but the difference here is that it's efficiently implemented. So control packets tend to happen infrequently, and so we don't need to have as much throughput as we would, say, the cheddar crossbar, which needs high throughput in between every point. And so the nice thing about the control crossbar is that it has an efficient mesh topology that's been implemented. Now for data packets, they go down through the static routing there. And with the static routing block, we have connections that allow for full throughput, but there is a loss of flexibility. These are static routes that they can't be changed at runtime. They're set up when this noc core is auto-generated. Now to really illustrate all these concepts together, let's look at an example. In this case, we're going to take our rfnoc Rx radio block in our flow graph at the top, have Rx samples go from there to the digital down converter block, and then from the digital down converter block back to the host through this rfnoc Rx streamer block. That is essentially allowing us to go from the rfnoc domain to the host domain. And you can see that domain switch there from the left. We have an arrow in green, and on the right we have that arrow in black. This is what the data flow would look like. And I'm just showing, say, data packets going through the noc core and the various rfnoc blocks. So we start off in the radio at the top. It goes into the static routing, which then loops back here to go into the DDC, which then goes to the stream endpoint, out the transport interface, the 1 gig E, to the host. Now let's add some complication to this flow graph to sort of illustrate the points here of how static routing interacts with flow graphs and the sort of limitations that it may introduce depending on what your flow graph looks like. So next, we're going to add an additional block in between the radio and the digital down converter block, the digital up converter block. Now this is kind of an unusual flow graph configuration and not really one that would ever be recommended. So if we look through the data flowing through our design here, we go from the radio down to the duck and then the DUC, the DDC, and then back out the 1 gig E, all going through the static routing, but we have a problem here. And that is that in the static routing, by default, there isn't a connection between the radio and the DUC and from the DUC directly to the DDC. There is no static route there because this is a really unusual configuration that you normally wouldn't see. So in the release images that come with our USRP devices, this sort of static routing topology isn't set up. Now the previous one with the radio RX samples to the DDC, that is an often used configuration all the time. Most flow graphs use that configuration. And so it makes sense to have that baked into our default images that we release. Now, how could we go about fixing this? Well, one option that we can see later on is we can edit that image core YAML file to define the static routing differently such that the radio can have a static route to the DUC, then from the DUC has a static route to the DDC. That would work just fine. Of course, one problem here is that this is an unusual flow graph, and what if you don't want to always have the DUC between the radio and the DDC? So there is another option, and I think this really illustrates how the stream endpoints come into play. Instead, what we do is we basically don't use any sort of static routing in this case. We essentially associate a stream endpoint with every block. So you can think of this almost as stream endpoint 0 is associated with radio 0, stream endpoint 1 is associated with DDC 0, and stream endpoint 2 is associated with DUC 0. And so what we end up is with a data flow graph here, and I've sort of color-coded it to show these sort of different data paths, but they all sort of loop back through each other. As we go from the radio to stream endpoint 0, so we go from stream endpoint 0 to stream endpoint 2, and then we go through the DUC, back to stream endpoint 2, then through stream endpoint 1, through the DDC, and then back out through the transport interface. Now what we've done here is we can rearrange these blocks now in any order we want. We can flip the DDC DUC, we can remove the DDC, we can remove the DUC, we can have all these different flow graph topologies. It's very flexible. But there's a trade-off here. And the trade-off is resource utilization and some latency. For full flexibility, we can give every rfnoc block a stream endpoint. And for those that are familiar with rfnoc3's implementation or have used it before, that's essentially how rfnoc3 worked. Although we didn't call it at the time, you could think of that every rfnoc block had a stream endpoint sort of internally in its NOC shell that we'll talk about later. And so, and all those blocks were connected directly to the cheddar crossbar. So every block could talk to each other directly, and you could have any topology, but that increased flexibility, of course, increased the resource utilization. And so if we want to decrease resource utilization, we need to set up static routes that make sense for our design so we can reduce the number of stream endpoints. Of course, the question might be, well, how do I know how many stream endpoints that I want? Why would I change them? I mean, in this case, it's showing, okay, maybe I want to rearrange blocks or remove blocks at will. That's actually one of the big reasons why you would want so many stream endpoints. In that case, you could use it for, say, debugging. So if you had a string of rfnoc blocks that you wanted to debug, and you had each one of them associated with a stream endpoint, then in that case, you could remove blocks at will or add blocks at will, and you could debug them individually or in maybe little groups. And so you get that sort of flexibility there that's really nice. So now that we've covered the NOC core, let's go ahead and move on back to the rfnoc block itself and start going through it piece by piece. between the NOC core and the NOC shell, which is covered by the text here, there's two types of AXI stream bus connections. One's in purple called AXI or AXI stream cheddar, and then there's AXI stream control. Now, the AXI stream cheddar bus for our rfnoc block generally will have data packets coming in, and you can think of, okay, what are data packets? What are cheddar data packets? What does this mean? You can think of it as generally as sample data that's been encapsulated in a packet. And one interesting thing about the blocks is that this AXI cheddar bus could actually be multiple buses wide if your block needs, say, multiple ports in parallel, that it wants to have multiple incoming and outgoing data streams or sample streams. Now the AXI stream control bus, that's for control packets. And what does that really mean, though, from your perspective? That's the interface that allows us to read and write user registers in your block. And if you want to know the nitty-gritty specifications of these packet types and their formats and what their timing diagrams look like, all those details are in the specification. I'm not going to go over them here because these are sort of at the peripheral of your block that you generally don't touch these interfaces very much. Next, we have the NOC shell. Every block generally has a NOC shell module in it. And this is sort of auto-generated boilerplate code that interfaces your block with the rest of rfnoc. In our case, when we create our game block, it was created for us, for our game block, via rfnoc-modtool. There's another way using rfnoc-create-verilog. That Python script lives in UHD. And what you do is you provide it your block descriptor or block description YAML file, and it'll auto-generate the NOC shell code. And actually will auto-generate, in general, your rfnoc block code as well for you based on what's in there. And so one question might be, well, why rfnoc-modtool versus rfnoc-create-verilog? Well, rfnoc-modtool, the nice part about it is it sort of creates this whole directory structure with all of your YAML files and everything, and your other files that you need for you sort of automatically. rfnoc-create-verilog, it expects you to already have created this block description YAML file, which we'll talk about later. But if you're new to rfnoc, you may not know, okay, what is this file? How do I even fill it out and specify anything? So that's why rfnoc-modtool is a bit more approachable when you're especially very new with rfnoc 4. So what does NOC shell do for us? So it packetizes and depacketizes these data and control packets, does clock domain crossing, and then it outputs a couple of buses for us that makes it easier for us to interact with these streams of packetized samples and coming into our block, as well as dealing with the reading and writing of user registers. So let's take a look inside of the NOC shell to kind of understand really what is going on here. One thing I didn't really show on the other block diagram is the fact that the blocks have clocks that come in from NOC core. They're called rfnoc cheddar clock, rfnoc control clock. These are actually defined in your block descriptor YAML file. These can be changed, but generally most blocks, this is what they're going to look like. rfnoc cheddar clock, or rfnoc control clock. They go into NOC shell, and the NOC shell derives two more clocks, AXI data clock and control port clock. At the end of the day, for most blocks I've seen, generally these are all derived from the same clock. They essentially are the same clock. That's not necessarily true. NOC shell can do clock domain crossing, and it may do it depending on the block or the USRP that we're using. But generally, that's what I've seen in most block implementations. And you can also have user-defined clocks. One you'll see is called CE clock. That CE standing for computation engine. That's sort of a term we use with rfnoc 3 a lot. That today we tend to just call computation engines rfnoc blocks. They are synonymous with each other. But you'll see CE clock here and there, such as like with the DVC and the DUC blocks. And even actually the game block, With rfnoc-modtool, it sort of auto-generates the CE clock in case you want to be able to use it. Next, we have a module called the backend interface. The idea here is Noc has a lot of information about your block, what its configuration is and its status. And that information is then relayed back to the host through essentially Noc core, or through communicating to your rfnoc block through this backend interface module. And what's in there are things like the Noc ID, which I said earlier, what is the Noc ID? Well, every block has a unique identifier, this 32-bit value that allows the blocks to be uniquely identified based on their, you can think of it as the block type. This isn't, say, a network address. This is more like an ID that is associated with your block that differentiates it from, say, a FFT block or the radio block. The game block, that we're creating here will have its own custom Noc ID, and you don't want these Noc IDs to be, they need to be unique. You don't want them to be the same as any other block, or UHD won't be able to differentiate this block is an FFT block and this block is the game block. Well, if they have the same Noc ID, it can't differentiate. So they do need to be unique. And the backend interface also has information about the status of the block in terms of, is it flushing data, and it's basically in sort of a reset state. What's the number of input-output ports? What are the buffer sizes? All useful data for UHD that you don't really care about because rfnoc is taking care of this information for you. The backend interface also creates two resets that are used by the user to reset their logic: AXI data reset and control port reset. Now in the middle here, we have two interesting modules called this AXI stream cheddar to AXI stream payload in context, and the other version of it that's actually the other way around, which is the AXI stream payload in context module to AXI stream cheddar. Just ignore the title there, that needs to be flipped. And so the idea here in Noc is that we have these AXI cheddar data packets coming in, and we don't, as a user, want to mess with AXI cheddar data packets. What we want to do is to have a nice clean interface where it's just a stream of samples coming in, and maybe some extra information like maybe some metadata about that sample stream, maybe like a timestamp, or is it the end of a burst, or how many samples are in a packet, just in case, say, packet size is important to us. And so that's what these blocks are doing for you in your block. They're taking this AXI stream cheddar interface and depacketizing it and then outputting its contents on two buses called payload and context. And it's also doing the reverse for you, which is you provided a sample stream in this sort of context, which I'll explain in the next slide here. And then it'll create this AXI stream cheddar data packet for you. So you don't have to worry about handling the rfnoc related packets and understanding the cheddar protocol here, packet protocol that is. Noc Shell is going to handle it for you. You just worry about your simple AXI stream buses there at the bottom. But it would be interesting to know kind of what is in a cheddar packet and what parts of it are we sort of looking at as what is this context versus the payload. Well, in the top of our little diagram here, we have it in kind of a, I guess kind of maybe a orange-ish sort of color here in the top. This is the context part of the packet. And in the first line, we have the 64-bit header here. And let's sort of go through here piece by piece as to what this means. So the first 6 bits is this virtual channels. This is an idea that would allow you to sort of route these cheddar data packets through the stream endpoints based on a virtual channel. That isn't right now, that feature isn't available. It's still a work in progress, but eventually it can give you some nice flexibility on being able to route your packets specifically based on sort of a virtual channel concept. and have these sort of parallel channels going through just one AXI stream cheddar data port. Beside that, there's EOV, 1 bit, that's end of vector. This is a new concept for rfnoc-4. In some cases, you may want to define your samples in terms of a vector of samples. One case might be like, say, an FFT, where you have an FFT size of, say, 512. So it'd be nice if every 512 samples you had something to tell you that this is like an FFT frame of 512 samples long. And EOV could be used for that purpose. Beside it is EOB, end of burst. Now beside that is 3 bits for the packet type. I've brought up the term AXI stream cheddar data packet, and data being the packet type of these cheddar packets. There's actually multiple types. I think right now there's 8 different types. And I'm not going to enumerate or go through them because generally you don't even really look at the data packet types. You might see this header here, but you're not really forming these cheddar packets yourself, so packet type isn't really that big of a deal generally to you. Beside the packet type, there's the num metadata. This is 5 bits here, and if you look just sort of 2 lines below, you can see this optional metadata 0. So another kind of new concept for rfnoc-4 is this idea that we can have metadata with our packets, or really associated with our sample data. And this is a nice idea. Say, it's really illustrated best with an example. Say you have a block where you are doing frequency hopping, and you say, okay, with this packet or this set of samples, I want to hop to this frequency. Well, you could include in the metadata the frequency that you want to hop to. And so instead of having to issue, say, a register write and try to issue that before the samples get there, make sure that the timing there and sequencing is correct, you can just include the frequency with your samples. Next is your typical sequence number that you see in any network protocol, our length in bytes. And then we have the dest EP, stands for destination endpoint or destination stream endpoint. That's sort of where we're routing this packet. One thing about that is that's controlled by the stream endpoint, so they'll replace that value sort of automatically, so it's not really anything to worry about. Now the next line, we see the timestamp. That's a 64-bit timestamp for your packet. And one thing I didn't bring up, but it's important to understand about metadata, is this is user defined. This is not something that Ettus is creating a specific format for the metadata. It's whatever you want it to be. After the context part of the packet, which is the header, timestamp, which is optional, or the metadata, which is also optional, you then have the payload of your packet. In this case, it's 64 bits wide, and it goes on for the length of the packet. So on this here, we can see that, okay, out of those modules, we then have our AXI stream buses, payload, context here on the bottom. And since I just explained, okay, the context part of our AXI cheddar data packet that comes in will be put out on the context AXI stream bus, and then the payload will go out on the payload AXI stream bus, and the vice versa is true when you're trying to output samples from your block. You'll need to put the samples on the payload AXI stream bus, and you'll have to provide a context on the context AXI stream bus. Now, one thing to sort of bring up here is, okay, well, shoot, there is a bit going on in that context part of the packet. How do I know to fill this out properly? Generally, most blocks will just loop back the context part of the packet. Now, this is a timing diagram of the payload and context packet. And this is what it looks like for both packets coming to you and the packets or the data coming to you on the payload and context AXI stream buses, and what it'll look like timing-wise for when you provide payload and context packets on those on the AXI stream buses that go into Noc shell. So the way it looks is you'll first have the context packet that comes out. And so in this case, you have these individual signals, AXI stream context eval. Now, one thing I'll bring up is the naming of this you'll see quite often as context and payload. There is a lot of flexibility in rfnoc now in how signals can be named with, say, Noc shell that are coming out. And so they may not always be named this. The block description YAML file may actually name these different. But I think in general, this is what you'll see. You'll see that there's an AXI-Stream context coming out, an AXI-Stream payload bus coming out with this sort of naming. Certainly on our custom game block that we're creating, this is the way it looks. So we have three values that come out, that the last one signified by a t-last asserting. And there's a signal that comes out, the t-user, that lets us know, okay, what is the meaning of each one of these lines? Because earlier when we look back at this diagram, we can say, okay, well, these lines kind of look, they're different, so how do I differentiate? How do I know which one I'm on without just counting or implicitly knowing? T-user tells you that, and so the first line, header, then timestamp, then metadata. In this case, it's only 3 long. There's 1 metadata. The packet did have a timestamp. So next, after the context packet comes out of, let's say, Nox-Shell, say we're looking at that bus that comes out of Nox-Shell. Next, we have the payload, which in this case is 3 samples long, D0, D1, D2 here, or I say samples could just be general data. It's really up to your rfnoc block and how the data that comes into it looks. And then the very last one is, the very last sample is, of course, signified by t-last asserting. And you can see here for t-ready, it wasn't ready the whole time. It came up sort of a bit later after 1 clock cycle. So you can see that D0 wasn't consumed until the 2nd clock cycle when it became valid. And just as a quick overview on the payload AXI-Stream bus, as I said, that every AXI cheddar data packet that comes in, we're going to get 1 context portion of it and 1 payload portion of it that's going to come out on those buses. Typically, for pretty much every block right now, the payload AXI-Stream bus is 32 bits wide, and you have SC16 samples coming out. SC16 format, if you're not familiar, for a 32-bit. For 32 bits wide here, it's the upper 16 bits are the real portion of the sample, and the lower 16 bits are the imaginary part. And then some important notes is that you must assert t-last when you are sending samples on that payload bus back into Nox-Shell. You don't want your overall packet size to be larger than the MTU, which is a value that's defined in your block. And we'll see that a little bit later when we actually look at our rfnoc block code. And it's also, I believe, in our block description YAML file. Now on the context AXI-Stream bus, just a bit of extra information here is, of course, there's still 1 context packet that's going to come out per AXI cheddar data packet that comes in, just like the payload side. And the packets are delineated by t-last, and you'll need to, of course, set t-last when you provide the context packet to Nox-Shell. And the metadata part, as I said before, just to emphasize again, this is user-defined. There is no set format to it. Next, we have another block inside the Nox-Shell called the control port endpoint. The idea here is that we have these AXI control packets that are coming in, and AXI control port converts this AXI control bus and the packets that are on it to what's known as a control port bus. And this is the sort of interface for reading, and generally it's used for reading and writing user registers in your block. Now those that have used rfnoc 3, you may be thinking, okay, well, they used to be called the settings bus. What happened to the settings bus? That's been deprecated to this sort of control port bus that looks in a lot of ways fairly similar to the settings bus, actually, with a bit more of a clearer definition as to how it really works. There is a bridge available, though, if you have say you have a block that uses the settings bus and has settings registers in it. There is a bridge called control port 2 settings bus that you can instantiate in your rfnoc block that will sort of do that conversion for you to the settings bus to and from. And if you want to look at an example of that bus being used, there is the keep one in block, does use that module. So if you need an example, that's a good place to look. So the control port timing diagram is here. And so here I'm showing sort of 2 transactions which are separate. These are independent transactions, but I just have them together in the same diagram. a write and a read. And so on the left here, we say, okay, if we're writing to our block, we send an exe control packet that's essentially a write. Then what we'll see on the control port is on our request write signal here, that'll get asserted. And this is a strobe signal. This isn't like exe stream where it's like tvalid. This is a strobe, a single cycle strobe here. And then we'll have on the address, we'll have the address of whatever we're writing to, generally our user register. And on the data line, we'll have the data to be written to that register. And then you'll acknowledge back with the request ACK signal asserting that, saying, okay, I've consumed that write. And that's important because if you don't acknowledge, that's going to sort of throttle back into this control port endpoint block saying, hey, I'm not ready for the next whatever transactions behind it. And say if you do a read transaction, it looks fairly similar to the write transaction, except you're doing a read request gets asserted. You have an address. Now, one difference here is instead of our request data coming in, we don't care about what that is because this is a read. We're going to provide the value. Generally, in the case of the value of our user register, we're going to provide that back, and that's on the response data bus here. So we would be setting the response data with the value of our register. I just said, okay, this data value is D1. One thing to bring up is the fact that our address here is 20 bits wide and our data is 32 bits wide. One thing is a comparison here to rfnoc-3 with the settings bus, is you may remember those that used it, that we had the first 128, it was an 8-bit wide bus, and the first 128 addresses were reserved for sort of what's going on inside Noc shell internals of setting it up and status and such. That no longer is true with control port. You have the full 20-bit address range. One thing that's not shown here is time commands. Conceptually, your block could have timed register reads and writes. Okay, so going back to our block diagram here, we went through Noc shell. And I showed in Noc shell we have these data, this payload data, AXI stream bus that's coming out in Noc shell in the context, and payload has samples on it. Context has at least cheddar header, maybe timestamp, maybe metadata. So next, below that is we have our user logic and user registers. Now there are a lot of options for how you can implement your user logic. HDL, Verilog, system Verilog, VHDL. You can include Vivado IP, FIR filter, FFT IP, turbo decoder if you want to get a license for it. The Vivado block diagrams are supported. So in one case that might be useful is you set up a microblaze instance and you do it through the sort of block diagram approach. You could pull that in this way. The tools support that. There's also Vivado high-level synthesis, so you can write your code in C or C++, HLS, and be able to have your user logic implemented that way. For the user registers, as I said, that generally that's hooked up to the control port, and it's pretty simple. They're there to sort of support the configuration and control of your block and provide a way of reading back the status. So having sort of gone through all of that, we're going to get now to the hands-on portion of our workshop here. And this is a block diagram of our game block as it looks right now, as it was generated with the rfnoc-modtool. As I said before, basically our block is sort of a loopback block. Our payload data comes in and it just loops right back in the Noc shell, the context data as well. And so essentially packets come in, samples, we don't touch them, we don't touch the context part of it either. We just loop it back and it comes out exactly the way it came. So we also have a user register too, and that's added automatically, but it's not used for anything. So we're just looping our data back, but it is set up. And the idea here is we'll take our payload data, it'll come in, and we'll split it into the real and imaginary part, or the I and Q part of the samples. We're going to have two multipliers here, one for the real part, one for the imaginary part. We're going to multiply them by a value coming out of our user register, and then send that data back to Noc shell. And in this case, we're not doing anything fancy here. We're not doing a rate change. We're We're not needing to mess with the header information at all or add metadata, adjust the timestamp, any of that. So we're just going to loop back our context data, which it already is, and so we'll just leave that part of the code untouched. So let's go ahead and give it a shot and start writing our own custom HDL. So we're going to open up our rfnoc block gain Verilog file, which is in the directory rfnoc-tutorial, rfnoc, fpga rfnoc block gain. And we're going to implement our gain in the user logic portion of the file, which is at the bottom. And in case you want to pause the video and give it a shot for yourself, here's a few hints here as to what we're going to be implementing on these last few bullet points in this slide. So I'm going to go ahead and open up our Verilog file for our block. So this is our rfnoc block gain Verilog file. At the top here for the module inputs and outputs and parameter definitions. We can see earlier I talked about the MTU, the maximum transfer unit here. It's set to 10, so that means that this block can accept cheddar, AXI-stream cheddar data packets that are size 2 to the 10th times 8 bytes long. 8 bytes being because our cheddar width here is 64 bits wide, or 8 bytes wide. We can see on our interfaces here we have our clocks. As I said before, rfnoc cheddar clock, control clock, and the C clock. We have this rfnoc core config and core status that comes from, or interfaces with the backend interface module within Noc shell. We have our AXI-stream cheddar data input and output ports. And then we have our AXI-stream control input and output ports. So here this is essentially our sample data coming in and out as cheddar packets, and this is generally our read and write register commands coming in and out from this port. And these are hooked up to the Noc core. Here we have our Noc shell gain. This is our auto-generated Noc shell that's customized for our gain block. Those generated by rfnocmodtool automatically. We can see our clocks come in. And then these are all hooked up at the input and output ports of our module. As I said earlier, we have these clocks, the rfnoc cheddar clock, rfnoc control clock. I said that they come in a Noc shell, and generally they just sort of come out. It just depends, though, if Noc shell does any clock crossing, which in this case it doesn't. So on the gain block. So in reality, these control port clock, if you were to look in the Noc shell gain, you'd see that rfnoc cheddar clock is connected, or control port clock, excuse me, is connected to rfnoc control clock, and the AXI-stream here data clock is hooked up to rfnoc cheddar clock. Here are those payload stream, context stream, in and out coming from Noc shell that our user logic will interact with. Here is the control port interface. Here's the user register logic. You can see here that we've defined our user register here at address 0. If we wanted to add another register, we could add it, just copy, paste here, maybe call it adder 1. We need to increment it by 4, not by 1. And then what you would do is in this case statement here, you would just, you could copy this and, maybe paste it here. And then, maybe we'd call this user register 1, and we'd create another one right here. And you could do the same in the write register. Now I'm just going to get rid of this because we're not actually going to use this code, so I'll just remove it all. But that's how you could quickly add additional user registers that you're reading and writing to within this logic. Then here at the bottom is our user logic. As I said before, we have our payload and our context actually stream interfaces that are coming from Noc shell. And by default, rfnoc-modtool, when it creates this file, they're just looping back on themselves. So we have the output AxiStream payload, AxiStream bus coming out of Noc shell, coming and looping back in on itself, and the same for the context AxiStream bus. Since our block is so simple, as I said before, we're going to just leave the context bus as is and let it loop back on itself. There's no need to make any changes here. Let's go ahead though and add our multiplier, or multipliers in this case, and add digital gain to this block. So first I'm going to create some wires for I, Q, and gain. They're each going to be 16 bits wide, so I, Q, and gain. I'm also going to set up some wires for the result of our multiplies with the gain. And then we're going to go ahead and set these values up. So gain is equal to the user registers lower 16 bits. I is equal to the real portion of our sample stream coming in, which is SC16, which means that that is the upper 16 bits. Q, which is the imaginary part, is the lower 16 bits. And then implementing a multiply, in this case, not the most efficient implementation here, but we can just use the multiply operator. Vivado will infer a multiplier here properly. Timing-wise, it may not do very well, but let's just do this simply and use the multiply operator. Next, let's go ahead and take these two and concatenate them, but we're going to use the lower 16 bits. So then that way our result is 32 bits and it's still SC16 because our upper 16 bits are the imaginary part and our lower, or excuse me, the real part, and the lower 16 bits are the imaginary part. Okay, so we save that file and we're done. When you implement your rfnoc block or your FPGA code for your rfnoc block, generally you also want to be able to test it, because generating an FPGA bitstream and trying to test it in the device is a very long and cumbersome process. So you want to go ahead and create a test bench to test your code quickly and iterate on it. The nice thing about rfnoc and rfnoc-modtool is the fact that there is a test bench infrastructure set up for you to make it easy to test your blocks. And rfnoc-modtool sets up a skeleton test bench for you with a lot of the code already filled out, and you can just sort of insert your test cases yourself. So as the sort of first step of setting up our test bench, and before we dive into the code, let's go ahead and take a look at another nice feature about rfnoc-modtool and how it sets up our out-of-tree module here by first creating our build directory and running CMake. So we don't have a build directory yet, so let's go ahead and create that, and we'll go in there. Now when we run CMake with our rfnoc-tutorial out-of-tree module, or any out-of-tree module that's created with rfnoc-modtool, what it needs, CMake, in our make files, it needs to know where the FPGA directory is for all the USRP code, which is in the UHD repository. And the reason it needs to know that location is it automatically uses some scripts in there to do things like run the simulation or build our bitstream for us without us having to invoke those scripts ourselves manually or write our own scripts to do that. So it's just kind of a nicety that's been added to the tool. So to point a CMake, or to let it know where our FPGA directory is, we set the variable here, UHD FPGA dir, and in our case, Just to show you real quick, if we go back here into our UHD directory, we can see that there's an FPGA directory. That's where all the FPGA code lives. And so all we have to do is just use this path right here. And then, of course, ... And that'll set up the make files for our rfnoc-tutorial outer tree module here. And also what it does is there's some extra code here within CMake to set up the make files to be able to interact with our test bench and run the simulation along with creating a bit stream. And you can see that here as at the output of CMake, we can see that it says, okay, registering rfnoc block. So there's a bit of code in our CMake files here that sort of finds this rfnoc block. And then we have a bit of code that says, okay, we're going to add a test bench. We're actually adding a target called rfnoc block gain TB, which will run our test bench. And then we're also adding another target, which is essentially going to use our image core here called gain x310 rfnoc image core. This will be used to allow us to build a bit stream with our gain block in it and some other blocks in it that I'll go over here shortly when we look at the corresponding YAML file. So since we set up a target here, we can run make, do rf and then tab completion, and we end up with rfnoc block gain TB. And let's go ahead and run it. I'll say right now that I expect that this will fail because what we've done is we've set up our blocks Verilog code, but we didn't touch our test bench. And by default, the sort of default implementation of rfnocmodtool is the payload and context buses loop back on themselves without any modification, but we modified it to apply a gain. And in good fashion here, the test bench makes that assumption, so that way out of the box you could run the test bench and it passes. But since we've added a gain, if we go up here we can see, okay, there's an error here. We received this, but we expected this, so it failed. Now, one thing before we move on to looking at our test bench code and correcting and fixing that error that was expected, but we're going to fix it, is I also want to show that there's a test benches target here. So if you were to add multiple blocks, each would have their own test bench, and you wanted to run them all at the same time, essentially back to back, instead of having to run make and then do it for each individual test bench target, test benches will call them all. So it's a nice little feature to know about there. Okay, so we'll go ahead and open up our test bench code, and we're going to make the modifications necessary to it to allow us to pass this test bench and have some more confidence that our block will work in the FPGA. So our test bench is in the rfnoc directory, FPGA rfnoc block gain, and the file is called rfnoc block gain tb.sv. Of course, TB stands for test bench, SV is system Verilog. This is a system Verilog file that's very typical for when people are writing test benches these days to generally use system Verilog. If you know Verilog, the nice part about it is it's basically a subset of system Verilog. So you can still use normal Verilog syntax, or if you do know system Verilog, well, it's available for you to use too. Okay, so here is the test bench for our gain block. Now there's some boilerplate in this code that helps us set up the test bench infrastructure. So we import some packages here. We have some configuration for the test bench. For instance, here's our NOC ID that was randomly generated. Maybe the number of inputs and output data ports on our rfnoc block. Here's some of the bus functional models. So this right here is essentially sort of setting up, you could think of as like a NOC core for us in our test bench without a full, complete NOC core, but just what we need for the test bench environment. Then we have our rfnoc block here, gain, that's our device under test. And then this is our actual test bench here. So first we start our test bench, we get the bus functional models running, and then we go through a series of tests. Some of these are just sort of boilerplate tests to just get basic functionality to make sure our block is alive and running at a very basic level. So we'll issue a reset, and then we'll just check some interesting values, the knock shell, the knock ID, make sure they match the values that we would expect. That way we know that we can at least, we're talking to knock shell, there wasn't, like say a clock isn't hooked up or something, or somehow we hooked up a reset somehow incorrectly and we're leaving things in reset. Or maybe knock shell didn't get generated properly. This is a nice test right here. Then next, these are the sort of the user test sequences in here. So the first one is reading and writing a user register. So we only have one user register, so it's reading and writing that one that's instantiated in our code. At first, we see, does it match the default value that we expect here if we issue a register read? One thing to note here is that we're actually referring to the address hierarchically by referencing the module instantiation here, rfnoc block gain. It's called, the instantiation is called dut. So dut period reg user adder. That's, of course, in our code as a local parameter. It's actually value 0. So this is a hierarchical reference here, and then the value ends up in read val, and then we check it with a hierarchical reference against what we expect. And we have an insertion error. So if these don't match, we're going to print this out. Next, we write a random value to that register with reg write. We read it back, and then we check and see if they're the same as what we expect. And we have end test here to, this corresponds with start test, so we're ending this verify user register test. This 5 microseconds here, this is like a timeout. So if for some reason you have a test case there's something wrong with it, or your code just sort of hangs, there'll be a timeout here that'll throw an error saying your test case took too long. The next one is just sending a stream of samples through the block and expecting that they come through unchanged. So first we set up a queue here, we call it send samples. We just put a bunch of random samples in there. We put SPP, that means samples per packet. That's okay. When we send packets to our block, how many samples are going to be per packet? They need to be smaller. This needs to be less than the MTU. And if we go back to the top of our block here with our test bench configuration, we can see that that's true. So our MTU, actually in the block, we sort of by default define it as 10, but here we say, okay, MTU is 13. That flows through, MTU right here. And that's 2 to the 13th samples, essentially. Actually, it should be 2 times 2 to the 13th, so 2 to the 14th samples. And our SPP, samples per packet, is 64. So yeah, we got plenty of space. That'll work, no problem. So we've set up our sample queue with some random samples, and we send them to our block with the send items command here. And then we can receive those values back and we put those into the receive sample queue here. And then we make sure, okay, did we receive the number of samples that we expected? And then let's go sample by sample and check that they match. And then there you go, that's it. And that's our test bench. Now let's fill out our test bench and have it go ahead and load the gain value from our block. So we're going to write a gain value. We'll go ahead and read it back from it, and then apply that gain value in our test bench to the sample stream that we're sending, or the samples that we're sending, and then check sort of our samples with gain applied to them in our test bench against the ones that we receive from our rfnoc block. So first, let's go ahead and set up the gain value here. And notice that here we wrote a random value to that gain register. Well, that's as good as any value, right? We don't really need to update the gain, so we'll just use that random value. But what we want to do is we want to read it from the device, or from our rfnoc block, I mean. So we'll create this signal here, gain, and we'll also read back the contents of our user register. And what we can do is, we can sort of put this read code wherever we want, but I'll just put it here with the rest of the code. So we'll say the block controller dot reg read, and I'll just go ahead and copy this up here. Okay, read from the user register and dump the value into user reg. And since our user register is 32 bits, and this is 32 bits, great. Then we'll say, okay, well, our gain is equal to the lower. Okay, so this should be the gain read out of our block. And then here in this loop, this is where we could add applying gain to our samples that we sent to the block, and then checking that the samples that we received back were appropriately multiplied by that gain, and checking that they match. So let's go ahead and create two more signals, or a couple more signals here. And this is basically going to mirror, what we did in the block. I'm calling this I samp and Q samp because we already used I as the, for iterating here. So I can't just call it I and Q. Well, I could call it Q, but I can't call it I. So, and then we'll do I mult Q mult. And it's just like in our block code. We'll say, okay, we have our send samples here. This is a Q. So this is the current value we're looking at, and then we want to grab the upper, and we'll do the same for Q except with the lower 16 bits. And then we'll implement the multiply just like we did in our block. And we'll go ahead and do the concatenation as well with the lower 16 bits. Okay, and that's it. So we'll go ahead and save our test bench. And let's go ahead and go back to the build directory and run our test bench again. And hopefully, if I've written everything correctly, this will pass. If not, well, then we'll have to do some live debugging and show the real usefulness of test benches. Oh, there we go. We went through our test bench here. We ran 4 tests, 4 of them passed. So overall it passed. Great. Okay, so it looks like our block does appropriately apply a gain when we set it. We verified it. Excellent. And just to sort of, make sure here, yep, it matches what I expected. So that's great. So we've written our rfnoc block, we've written a test bench. So there's other things we need to do in software and in GNU Radio, but before we do that, we need to build an FPGA image that has our block in it. Now, the tool to do that is called rfnoc image builder, which, if you're familiar with rfnoc 3, it used to be called UHD image builder, and there was a GUI associated to it. This has been changed now to what's called rfnoc image builder. It's a command line tool. I think in the past you may have seen that there's a GUI that is sort of related to this, but that's still coming in the future. That's a work in progress. So right now, that just the command line tool exists. for building these bit streams. It requires a YAML file that's an image core YAML file. Is usually the terminology that's used for that specific file. And what is in this YAML file is basically directives that are saying, okay, this is the device and target that we're building against. This is the rfnoc blocks that we'll have in there. This is the stream endpoints. You know, what stream endpoints, how many are we going to have, what are they going to look like, some configuration values for them. What are the connections between the rfnoc blocks and the endpoints and any other I/O that our rfnoc blocks need. And so this connections part is really, we define and set up those static routes that I was talking about earlier. And then also defining clock domains and what clocks are hooked up to our blocks. Now rfnocmodtool automatically created an example YAML file for us. That's here in the rfnoc directory icores, this gain x310 rfnoc image core.yaml. And also, you can see here that for building our bit stream, we actually do make that file without the .yaml at the end. And so by default, this image core is targeting the x310 with the x310_hg target. What does this target mean if you haven't really done much on the FPGA side of USRPs or building them? If you were to go and manually try to build or if you're going to try to build your own image by running the make files in the FPGA directory in UHD, you'll see that every device has like a set of targets. And those targets have certain meanings. For the X310, for instance, the _HG image is called the hybrid image. What that means is this image will have a 1 gigabit Ethernet. One of the SFPs will be for 1 gigabit Ethernet. The other one will be for 10 gig E. And of course, they'll also have PCI Express. They always have PCI Express. There's also an image called XG for dual 10 gigabit Ethernet. And these are different, say, for the N300 series. They have similar nomenclature. Actually, that's fairly similar. But that's what it means when it's the target. It's actually referring specifically to the particular target that's associated with those make files. And then in this YAML file, we have our rfnoc blocks, which by default, it has sort of the useful ones that are the radio, DDC, the DUC, and we automatically adds our gain block. That's, rfnocmodtool is trying to make this simple for us, so it sets it up for us automatically. Now let's go ahead and take a quick look at that YAML file. So I'll go ahead and navigate there. Here you can see it. And I'll explain a little bit of what's going on in here. So we have some of these general parameters. Here's our device, X310. There's the target. Here's our stream endpoints. If you remember from our earlier our earlier block diagram, you can see that there were sort of 5 endpoints set up, and so these are the 5 endpoints. Here are our NOC blocks that our rfnoc blocks that we're going to be including in our design. Here's, as I said before, we had the radio 0, radio 1, DDC 0, DDC 1, DUC 0 and 1, and our gain block, and these are the YAML files, associated. They're called, what they're called, gain.yaml, etc. Here are the connections. So this is our static connections in the design here, our static routes. So reading this, some of the comments here are fairly helpful. So one route I talked about was from the radio through the DDC back to the host through stream endpoint 0. Well, here's that case right here, radio 0 to endpoint 0. So static route, radio 0. It has its source port out 0 here. You can find these defined in their block description YAML file, which we'll look at later on our game block. So we have radio 0 source port, it's out, destination block DDC 0, it's its input or destination port called N0 here. And then we go from our DDC over to stream endpoint 0. So there's that one static route. And earlier I said, okay, well, if we threw the DUC in there, the DUC 0, it wouldn't work because the static route isn't set up. Well, here we can see this right here is the DUC route. It goes from endpoint 0, so coming into endpoint 0 from the transport, from the host, into endpoint 0. Contrast this with, this is source port, endpoint 0. Here, this would be coming out of it. So in this case, it's going into it. We go from there to the destination block DUC 0, and then from DUC 0 to radio 0. So if you kind of think about it, it's almost like it's basically the opposite direction here. From radio DDC to endpoint, we're going endpoint to DUC to radio. So this is the RX case here. This is the TX case where you're sending transmit samples to the radio. So you want to go to the DUC, to upsample them to the right sampling rate for the radio. And that static route is incompatible with, conceptually, if we try to put the DUC in between the radio and the DDC. There is no route defined here. And we could edit this to add that route. But as I said before, if we really wanted that functionality, well, what we'll do is we'll just have every block correspond with an endpoint, a stream endpoint. And then that way we can interchange these at will as needed. Here's our gain block. In this case, we're going straight with an endpoint. So this allows us to put our gain block, we could put it after the DDC in this case, or we could put it before the DUC in this case. And then here's some additional connections to set up some special ports that are on these certain blocks, like the radio block. Then on the bottom here is clock domain. So this is setting up clocks for our blocks. In this case, it's adding that CE. It's a little hard to see here with that. Here you go. So here we can see on our gain block, we have our CE clock that's set up here. Okay, so that's what our image core YAML file looks like, the one that was made by rfnoc-modtool for our gain block. This is what it looks like from a block diagram perspective, with our auto-generated NOC core here in the middle, transport interfaces on the left, rfnoc blocks on the right, and our gain block there at the bottom in yellow. At the top here, you can see a sort of example flow graph in GNU Radio of a signal source sending data through our gain block and then coming back out to be plotted by a time sync. If we focus in on our gain block, if you look into that, when we were looking at that YAML file, we saw that there was a route between stream endpoint 4 to our gain block and then back. So in this case, it's more of a direct connection there through the static routing. Now, say we wanted to take our gain block and have it on the output of the radio DDC flow graph that we had seen earlier. So we go rfnoc RX radio through rfnoc digital down converter block, and then through our rfnoc gain block here in the top here in our GNU radio flow graph, and then we just say we plot that with a frequency sync in this case. What we'd see here is we'd involve sort of our one part of the flow graph here, the radio and the DDC, and then our gain block, and we'd have two stream endpoints. Now the reason being here is that the radio block the data path from the radio block would go through the static routing and then through the DDC, then to stream endpoint 0. And then from stream endpoint 0, we go through stream endpoint 1, through the gain block and back in and out 1 gig-e. And this route works perfectly fine. And this sort of shows, in this case, that we have 3 rfnoc blocks but 2 stream endpoints. That's because for rfnoc, the radio and DDC rfnoc blocks, they have a static route and they're associated with stream endpoint 0, as we saw in the YAML file. And then the gain block is associated with the stream endpoint 4. And the nice part with this setup here is that with the game block, we can test it individually by itself and sort of debug it. And then we can also hook it up to the output of our digital down converter block there too, to work on real samples coming from over the air. So that concludes the FPGA part of the workshop, or the part of the discussion that focuses on the sort of development we need to do on the FPGA side with our block HDL and our test bench and how to run the simulation and how to build an image. Next, we're going to cover the UHD software part of rfnoc and how that interacts with our block through the block controller C++ code and that block description YAML file that I've brought up several times. We'll dive into that as well. So first, let's start off with our block description YAML file. It tells UHD about the block configuration and capabilities, configuration-wise, NOC ID. It tells us where our HDL source is. It also describes input clocks, block parameters, block I/O, and of course rfnoc-modtool created a skeleton file for us. And everything's set up already for our gain example. We really actually don't need to change anything, but I'm going to go ahead and take a look at this file with you. So it's in our rfnoc blocks directory here, that gain.yaml. We'll go ahead and open that up. Okay, so at the top of the YAML, the block description YAML file for our gain block, we have here is the NOC ID that was randomly generated. We have this interesting bit right here called makefile_sources. So when you're running rfnoc image builder, you're not telling it where the source is for our block. It somehow seems to know where it's at. We just tell it in our image core YAML file, hey, we're going to use gain.yaml, and then somehow all the sources are brought in. Well, this is the missing link right here. Here in this YAML file, we also define the clocks for our block, the input rfnoc cheddar clock, control clock, and the CE clock. We define our control interface here, it's control port. We define our data interfaces. Our block only has one input and one output data interface, so just one in and out. We could, have multiple. You could copy and paste this and name it something else other than in, maybe in1 or something like that. And so you could have multiple inputs and multiple output data streams, and that would look like for our block. It'd be multiple AXI stream cheddar ports. Now, in this case, if when you make the edits to this file, they're not going to automatically, reflect with our block with rfnoc-modtool. rfnoc-modtool doesn't have that capability. So if you were to try to edit this file, and then you would need to pull this in with the earlier Python script I talked about called rfnoc-create-verilog. You would pull this block descriptor YAML file. You would use that as an input to that script, and then it would create the updated NOC shell, and actually it would create some other sort of skeleton files that you could use to update your rfnoc block code. So that's the block descriptor YAML file. And just to kind of show you with our block diagram, how do values within the YAML file correspond with what's in our block, via this block diagram here. The NOC ID that's in NOC shell that we saw, or that you can see if you go into NOC shell, you'll see that the NOC ID is defined in there. They're the clocks that normally aren't on the block diagram, but they're coming in from NOC core. Here, we have our sort of control interface coming out of NOC shell, and then we have our, payload and context sort of interfaces here. So with our block, we have our block description YAML file. Then we also have a block controller C++ file. And what that's doing is it's C++ code that is our software control interface for our rfnoc block. It's what we use through the UHD API to communicate and control our block. One of the ways that we do that is by creating properties, which allow us to access user registers and force block I/O requirements, such as our inputs and outputs data types need to be SC16. So say we hook up with another block that uses a different data type, we'd have an error. And also the ability to sort of propagate updates to other blocks. So if we change a user register in our block and for some reason it may affect another user register, we'd have that ability to propagate those updates through other blocks via these properties. Our block controller also allows us to expose customized methods for our block that allow us to do interesting things, such as like an FIR filter rfnoc block. We could set the coefficients for that block through set coefficients. In fact, if you look at the FIR filter block controller code, you'll see that this is lifted straight out of the code as there's the set coefficients method. And rfnocmodtool, of course, generated a skeleton file for us. Everything's already sort of set up because our block is so simple. And let's go ahead and just dive in, though, to that C++ code, and I can give a bit of an explanation as to what's in there. So if we go to the lib directory, we can open up our block controller code here. So here's our user register here, and its address and default value. We can see that this inherits, from this gain block control. Well, where is that defined at? We actually go into include tutorial, and we open up this file. We can see that, okay, here it is, and it's actually inherited from noc block base. And that of course, is in UHD itself. You'd have to go into UHD to see the code for that. For our block, we have for our constructor, we have this sort of macro that does some stuff to set up our block. If you look at the bottom here, you can see that there's this UHD register block direct. Normally, there isn't too much that you wouldn't really touch this, other than the fact that if you maybe change the noc ID, you might edit this there. And then within our block, we're going to call this method register props for register properties. And so now we have a bunch of properties on our block in this case, we really only have 3 that are there in this case. So we have one which is, okay, we have a user register here, set up here a property for it. We're calling it user register. This is a string that you can refer to it through the property tree. We give it a default value. And here what we'll do is we can basically access this property such that we'll get the value, we can get the value for this user register here, and we can then poke the user register in our FPGA, our rfnoc block in the FPGA, and set it at this address, which is address 0 here. And then we have, they call these register, these edge properties. This idea, as I said before, is that our block can enforce what sort of data types it interacts with. And so in this case, we define it as SC16 for, in and out. And so if for some reason other blocks are made that have different data types, that they consume different types on their sample data coming in and out, this would, in those cases, catch them and say, okay, we can't hook up our block to another block in a flow graph because the data types aren't compatible or the same. Now, in our actual list or library of rfnoc blocks, they all pretty much use SC16. So generally, this isn't an issue that you'll run into. So in our case, for our rfnoc block, we just have our user register. We only have one. That's the only one that we're interacting with. So we don't need to make any modifications to this block controller. It's going to work out of the box for us. Now, one thing I also want to bring up, and this is really a great feature of rfnoc 4 that we didn't have in rfnoc 3, is support for Python bindings for our rfnoc blocks. Now, most blocks have these already available in tree, the blocks that are in the UHD tree. And for our gain block, if we were to create a Python script to sort of access our gain block through Python bindings, this is what it would look like. Now, I do have to say one thing about this though, is the fact that we haven't managed to get rfnoc-modtool set up yet to generate these Python bindings for you automatically. So unfortunately, while we have the code here, the support for rfnoc-modtool generating the bindings automatically is coming, and so this code right now is just more for a reference. You can't really use it with the gain block right now. But you could look at it and see, okay, so we're going to create, our TX and our extremers here. We're going to create an rfnoc graph. We're going to get our block, our gain block. We're going to poke a register address 0. We're going to connect up our block and send some data through and receive that data back. So this has everything we need. It's just we got to work on rfnoc-modtool a little bit to sort of set this up for you automatically. The Python bindings, that is. And then one more thing that I want to mention on the software side for UHD is the fact that while this has been really focused on GNU Radio flow graphs, and the rest of this workshop will be also focused on GNU Radio integration with your rfnoc block, you can also create just a C++ application that just uses the UHD API and doesn't touch GNU Radio or need GNU Radio at all. Now, of course, if you're using rfnoc-modtool, you do need GNU Radio because that's what's going to be used to set up that out-of-tree directory structure, and that relies on gr-ettus, which of course relies on GNU Radio being installed. But in this case, we have you covered when it comes to having sort of an example design already existing, so you don't have to worry about having or using rfnoc-modtool and having GNU Radio installed. What you can do is go to the UHD host examples directory. There's an rfnoc example that's actually another gain block example in there. And so you can build off of that for your UHD C++ API only sort of block that just uses C++ and not GNU Radio. And that pretty much covers the software side of our rfnoc block when it comes to UHD. In our case, a lot of the defaults and everything, they were pretty much all set up by rfnoc-modtool, and our block is simple enough that there really isn't much going on there that we need to make any updates to any of the files. So next in our stack here is our GNU Radio integration, and how do we get our block sort of into GNU Radio and running there, and what are the associated files? So when it comes to GNU Radio blocks, they're written in C++ or Python. And a question that might come to mind is, well, then how does GNU Radio interface to rfnoc? And earlier, I'd said that gr-ettus is sort of that method, but how does that really work? Well, there's infrastructure code in gr-ettus written in C++ that sort of exposes rfnoc to GNU Radio, or sort of adds it. And what you do as a user is, in the C++ code, there's a class for blocks in there that has sort of the code in there to make it look like, or to make it a GNU Radio block, but also work with rfnoc. And users extend that base class and then customize it for their rfnoc block. In general, though, most blocks can sort of use this base class as is. It has some built-in methods that allow you to set the properties of your block, which we had just seen in the block controller. For instance, in our gain block, we have a property to set the user register. So in our GNU Radio block code, we could just use this built-in method to set that property without having to write any special methods to do it directly. And we'll see that this is a really nice little shortcut that we can use with our grc YAML file to really make it easy to interact with our block without having to write a lot of C++ code. As usual, rfnoc-modtool will create a skeleton file for us, but we don't need to modify it at all or really do anything with it, because we're going to use basically the rfnoc base class, within gr-ettus as is, and use those built-in methods to set properties. I'll go ahead and open it up real quick so we can just take a quick look here. So it's our gain_impl.cc file. We open it up here. And then there isn't too much really going on here. You can see that we get a reference to our block this way. But let's open up in the include directory this gain.h, and we can see that, okay, for our block, our gain block, we're inheriting from here, gr-ettus rfnoc block. And so this is that base class that does a lot of the, or has a lot of the code, or pretty much all the code that we're going to use to have our block run in GNU Radio. And let's go ahead real fast and open up that code, which we can see right here, rfnoc block, you can see right there. So let's open it up. And there's a lot in, well, in this case, actually not too bad. We have a work function in here. And so you could go through this code and the other code that's in gr-ettus to sort of understand how does this base class work, and how does it allow us to do things like have these set property methods. It's definitely worthwhile to take a look to see what sort of capabilities your block in GNU Radio can have sort of out of the box. So next we have the GNU Radio companion bindings that are written in YAML. And so what this does is it describes our GNU Radio block to GNU Radio companion. And the nice part about it being in YAML is no recompilation, so you can just change it on the fly. This is a requirement of GNU Radio companion, but not strictly of GNU Radio. There is info on the gnu-radio.org wiki about these YAML files and what's in them and how to edit them. I'm not going to go over it here. What I will say, though, is that, of course, we have skeleton files generated, and let's go ahead and dive into that real fast, since there's some interesting tidbits in there. So we'll go to the grc directory. Here is our YAML file. Okay, so our block is called rfnoc gain. We import our block here. And this is sort of just some boilerplate code to set up the gain block. Now here's that part I talked about where we can set our user register by setting the property and using a built-in method to set that property without having to write any custom code. Because if you looked back at our C++ code for our GNU Radio block, for our gain block, you'd see that there is no set int property in that code. That comes from the base class. And then we set user register. See how this is a string? If you remember before in our block controller code, we called that property user reg. And so here we're referring to it by its string name here, user reg, and we're going to set the value here. We also have a callback set up, so when we're running our flow graph and we adjust the gain while running the flow graph live, it'll automatically run this code. And rfnocmodtool automatically set us up one parameter here for our user register. It's an integer, 32 bits. And so that's this right here, actually, this parameter is set up for us automatically. And our block has an input and an output. Its domain is the rfnoc domain. That's why those arrows are green. And we have labels in and out, and its data type is C16. So that's the YAML file for our GNU Radio companion bindings for our rfnoc gain block. That's also the last step related to getting our rfnoc block up and running. So in the FPGA, we've implemented our Verilog code along with a test bench, verified that our block seems to be working, at least in a test bench environment. In UHD, we looked at the block controller and the block description YAML files. And then in GNU Radio, we looked at our block code and the GRC bindings in YAML. And all of this comes together to realize our rfnoc block. And so the next step is that now that we have everything up and running, we will go ahead and build our out-of-tree module, our rfnoc-tutorial out-of-tree module, and then install it. And we'll also program the bit stream that has our gain block in it to our X310. Now, let's first start off with the installation here. So we'll go to build. Now, I've already ran make here, so it's already done building. And then I will go ahead and install. Now it's installed. And one thing earlier that I didn't really show is running this make gain X310 rfnoc image core file, or image core target, excuse me, that will build our bit stream for us. I can go ahead and run that now real fast just to show you that in this case it'll error out because in this environment that I have set up I don't have that full license. And so it should give us an error here shortly. Here it is in red saying we do not have a valid license. And then it'll error out eventually, but I'll cut it off right now. So what I've done is I've actually built this in my normal environment and built the bit stream. And I've loaded it up on my USRP, my X310 already. But in case you built the bit stream yourself and you're wanting to know just real quick how to load it, if I go over to the desktop here, here's my bit stream, and we would run UHD image loader, args equals, and we'll say type X300. Then I would say FPGA path equals. We'll get this to autocomplete for us. There we go. Then we can just say right there. And I'll go ahead and just let this load again. And this will take a while, so I'll go ahead and again pause the, like I did earlier, pause the video and come back when this is done loading. So the bit stream has been loaded, and my X310, I've reset it. So for our next step, what we'll do is test our block in hardware. And what we're going to do is open up GNU Radio Companion and load our gain.grc file, our example gain flow graph that was generated by rfnocmodtool. And what I expect to see is we have a signal source coming in, going through a gain block, and then being plotted on a time sync. So we should see a sine wave that we can adjust the gain, adjust its gain using our rfnoc gain block. So first, let's open up GNU Radio Companion. And it already has our gain block opened here. But as you can see, it's in the source rfnoc-tutorial examples gain.grc block. It's already open because I've opened it before. And then what we can do is we can run the run button here, or do run execute to run our flow graph. So here we go. This is running on hardware right now. So this is our sine wave. I'll go ahead and dial back the frequency sum here. There we go. And here's our user register that we can adjust. And right now it's just set to 1. And then we have the amplitude of our sine wave here. Now what I'm going to do before I start adjusting the user register is I'm going to dial this back until it's really small. And the reason being is that with our user register here, I don't want to cause, well, there we go. I caused the arithmetic overflow right there really easily. So let me control this way. So here you can see I'm updating our user reg by adjusting the slider here, and it's increasing the amplitude. However, we don't have too much range here before we cause arithmetic overflow. In fact, you can see our amplitude is 0.01, and so once we hit 100, you get overflow. And so our user reg is working, gain is working through our block, so our block is complete, it works. And the neat part about rfnoc is the fact that these updates can happen super fast. I can change the slider really quickly. It updates, basically instantaneously here. And that's pretty much it for our block here for what we can do with it. So I'll go ahead and close out. And there's one more thing I want to show you here in GNU Radio Companion. Here on the right side we have our list of blocks here, and you can see on the bottom we have 2 additional categories, one for gr-ettus. We have an rfnoc category here. You go into blocks, and you can see, okay, here's where our rfnoc blocks are: the digital down converter block, digital up converter block. We have our fast Fourier transform, FFT block, our phosphor block, RX and TX radios, our RX and TX streamers. And then here's our tutorial category here, and we have our rfnoc gain block. Okay, so that concludes our workshop here on rfnoc 4. And as a final takeaway, I'd like to say that rfnoc is for FPGAs as GNU Radio is for general purpose processors. They're both infrastructures for SDR applications. They handle the movement of data between blocks. rfnoc does it on the FPGA, so it's actually stream-based. GNU Radio does it in software. They try to take care of the boring and repetitive, recurring tasks that happen when it comes to designing these sort of DSP, SDR applications, dealing with flow control and addressing and routing data. And so they try to handle that for you. They both provide a library of blocks. GNU Radios is huge, and rfnoc, it grows every year. They both have what you can think of as a graphical front end. GNU Radio is GNU Radio Companion, and rfnoc is still GNU Radio Companion, essentially through an out-of-tree module, our GRS out-of-tree module. They're both open source, but one thing to understand is neither one of these infrastructures write your blocks for you. You'll still need to on rfnoc, go into the FPGA and write your FPGA code. Just with GNU Radio, you'll need to do your implementation and software in C++ or Python. But they do make it easier, faster, less error prone, and also allows you to create designs that are more reusable and more composable than in the past. And now with rfnoc 4, this is better than ever. I appreciate you taking the time to go through this workshop, and if you have any questions, we're available anytime. Support@ettus.com or the mailing list. And I hope you enjoy using rfnoc and get a lot of value out of it.